Hey there, I'm with Merlin Blau, and he put together a
Right.
paper or a project on singing synthesizer based on PixelCNN, and I listened to some of the audio files. We'll listen to these in the future, but I'd love to learn more about what you were doing to inspire this work. What were you working on?
So I've been involved in this kind of area of singing voice analysis, processing, and synthesis for the last couple of years now. So, and mainly on the signal processing and kind of techniques based on unit selection. So using like kind of recording a singer and then chopping it up and concatenating stuff, but not so much machine learning. So this is an area that we didn't focus on so much. We did some stuff with like HMMs, for instance, which is kind of a simpler model.
Do you know what HMM stands for? Sorry, I'm not.
Yeah, sorry. It's a hidden Markov model.
Oh,
So
okay, okay, yep.
so then this year or last year I should say, when the Google WaveNet came out, we were very much impressed by what this model could do. So this was a model that could synthesize speech from text, but on a sample by sample basis, which is really a step beyond what was possible up until that point. And it was especially interesting for us because of the techniques that are based on machine learning, for instance, singing synthesis or even speech synthesis, they tend to suffer from a problem called oversmoothing. So if you compare it to the techniques that we're used to working with these things based on samples, such as the unit selection, machine learning approaches tend to sound much more kind of muffled and very smooth, and they lose all the kind of rich detail that a recording has.
So like too smooth of a transition because it's trying to kind of make everything.
Yeah, exactly. Yeah. So so then when the WaveNet came out, we saw really for the first time that it was possible to use machine learning and really preserve all this detail and really have very good quality. So we became kind of excited to try this also for singing voice.
So are you kind of a music person traditionally, or is that your background, or is it something that you just kind of applied to? Like, how did the music part of it come into your career?
I studied music technology, and I focused more on kind of the software development part and signal processing. And now I'm at an institute called the Music Technology Group in Barcelona, and where the focus is completely on applying technology to sound and music.
Cool.
So doing all kinds of tasks related to that.
And so did you have a developer background, or were you self-taught programmer as it related to the kind of your academic pursuits? Tell me a little bit about that process.
Well, I started out more in a development position, and also doing some more research activities on the side. And yeah, like the last maybe 12 years or so quite a long time, I've been involved in an industrial project with a company called Yamaha from Japan, working on singing synthesis. So they have a product out called Vocaloid. I'm not sure if you ever heard of it, but it's a singing synthesizer. So people can enter lyrics and then enter notes and select the singer, and then have the computer sing it for them.
Wow, that's really cool.
Yeah, and especially in Japan, this has really taken off already around 2008 or something. It became really popular, and many people started incorporating these virtual singers into their music, and also there was an audience for people that listen to this kind of music. So yeah, so that's why I'm working on this.
Yeah, no, that's really cool to hear about. I'm not familiar with the concept, and so it's I can think of a lot of different applications of that. It's pretty cool to hear that that's out there in the real world. And so it sounds like that type of technology was out there, and then when you guys ran into this kind of more machine learning approach, you said, hey, let's try this out because of that this smoothing piece.
No, not really. So the technology that's out there already, it's kind of based on samples of a singer, which it's kind of good because you can get good quality relatively easily, but it's hard to really go much beyond that. So it's not very flexible.
Got it.
So a machine learning approach could really improve that aspect of it.
Cool. So take us through a little bit about what the research is and kind of why this is interesting and why you put it together as a project and what's different. You've touched on some of those pieces, but take us through. And I'm going to share my screen with some of the actual project file that you have, and that might give some good context for the audience. So just a second here. Can you see my screen?
No, I cannot. Oh, yeah, exactly.
Okay, you can see it now?
Yes.
Great. Okay, cool. So take us through a little bit of what this project is, at least in your own words.
Okay, so so like I said, it's inspired by the WaveNet, which models sample by sample. But for singing voice, it's hard to do this to apply exactly this approach because you have the lyrics and pitch that kind of combine to create a very big space to sample. So if we would want to model at a sample level, sample by sample, we would really need a lot of data to model all the pitches and all the phonemes together. So what we did was use something called a vocoder, which splits up the voice signal into a pitch estimate and also a spectral envelope. And some aperiodic part. And then this spectral envelope is the part that we model. And it's you can kind of think of this as a image. So it's 2D data where you have a frequency axis and a time axis. And then the intensity of each pixel in this image corresponds to energy at that specific frequency and time.
And so is that kind of the graph in the upper right area where the blue and green area?
Yeah,
okay.
Those three are examples of.
So you're kind of thinking about this, and you said from a did you say 2D perspective?
Yeah, exactly.
Right.
So this is kind of like an image. So then we thought, and the good thing about this is that it separates pitch and the spectral envelope, which corresponds to phonemes.
Cool.
So if things split, we can synthesize any lyrics at any pitch, basically. So then to model this image, we used a model called PixelCNN, which is kind of a predecessor to WaveNet. So it's kind of a 2D version of WaveNet, and it actually came before it. So, but still very similar. So how this works is that it models each, instead of sample by sample, it models each pixel by pixel. And then you train a model to predict the following pixel based on a window of previous pixels.
Interesting.
So, yeah. And then at synthesis time, you also do a synthesis pixel by pixel. So then it's a kind of autoregressive process where you predict, and then from those predictions you make another prediction, and so on until you have the complete signal.
Interesting.
And then another aspect is that we want to condition it on in this case, the lyrics that we want to synthesize and the durations of each phoneme. So in this kind of the figure here on the left with the diagram, you can see that on the right hand side, this is kind of a control input that determines which phoneme should sound at which time.
And and when you say that, and that's kind of this idea of saying, hey, I want these lyrics to be these types of lyrics, and then is that what the lyric is translated to? Is these control inputs?
Exactly. So yeah, here you see like it's a one-hot encoding of the phoneme. So it's just all zeros, and one value is 1, and then there's one for the current phoneme, one for the previous phoneme, and one from the next phoneme. And then there's also some information related to the position within the phoneme.
Interesting.
So,
yeah. Cool. And so it says that the data set you said was, or at least in the project, it said 123 shortened sentences, around 10 minutes worth of data. So that type of data set, which is not that large of a data set, it was able to then generate this singing synthesizing. Is that like, take me through a little bit of what this data set and its size means as it relates to the work?
So yeah, first of all, yeah, it's true that it's very, very small data size, especially if you compare to like typical speech synthesizer, text-to-speech, which might be several hours. So this is very short. But I have to say that it's first of all, it's in Spanish language, which is in some way a bit simpler to English because of there's only 5 vowels, and like also the consonants and vowels are more separate and more, well, it's a bit different. And then what we did was record a singer, and in this case a female, that sings at a constant pitch and then follows a set of scripts. And so all of these sentences are sung without any pause, at a constant pitch, at a fixed rhythm. It's like na 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 na. And then from this data, we segment the phonemes, and then we train the model with this. We extract the acoustic features and these linguistic features, and we train the model with it.
Cool. And so I think one of the questions I was trying to drive at is that feels like a small data set in a good way, in saying of like, hey, if you're able to record an artist doing this much work, and I don't know how long it takes to actually record that session. Does it take an hour? Does it take a day? Like, how long does that take to build a data set like that?
So in this work, we only use the single pitch. So normally we would record several pitches to have a kind of bigger range of things. But these 10 minutes, maybe they will take an hour to record.
Cool.
Okay. I have to say that these 10 minutes is with all the pauses cut and like all silences are removed. So it takes quite a bit more to record than the data that you actually use.
Yeah. Okay.
But it's few data, and actually overfitting is an issue with especially with this type of model, because it's very easy to have a lot of model parameters.
Let me take a moment to say that this wouldn't be possible without companies like Amazon.com. If you have experience with machine learning and are looking for a new challenge, they have over 100 opportunities available. Be sure to check out the link in the description, and let's get back to the show.
I was going to actually pull up the other file, which were your actual sound examples, and
Okay.
an example of that.
So I have to say that the differences between these are quite subtle. So especially if it's kind of recorded on the stream and people are listening back to it, I'm not sure how well the differences come across. But well, there's two different songs. Both are in Spanish. So the first one is with background music, and the second one is without background music. And so it was my intention that, so first of all, to show that this method can achieve kind of quality similar to the state of the art, which might be unit selection. and also that it's a bit different from HMM. So like I mentioned before, the HMM one, the Markov model, it tends to sound very consistent, but also very smooth. And some of the consonants are kind of smoothed out, and some of that detail is preserved in the PixelCNN one. So yeah, I think you could play them in just the order that they are. So first PixelCNN, and I would just play a small portion because it's quite a long example.
Como casi siempre, cuando algo se muere, nace la nostalgia.
On to the HMM one.
Como casi siempre, cuando algo se muere, nace la nostalgia, buscando un corazón.
And unit selection.
Como casi siempre, cuando algo se muere, nace la nostalgia.
Cool. So what I was trying to listen to, and it might be helpful if you share this in kind of insight for the audience as well. When they're listening to these examples, what should they be particularly paying extra attention to? Is it trying to listen between the differences of kind of the little short sentences? Like what should they be really focusing on?
So yeah, I have to mention that in these examples, in all cases, so the pitch and the timing comes from a recording. So in all of these examples, that part is exactly the same. So the only part that changes is the timbre. So the sound. And then the main thing to listen to, I think, is kind of the overall impression of quality, and also this over smoothing problem. So, but it's kind of difficult for me to because I'm very used to listening to these kind of examples. So for sure, I will pick up on things that most people will sound exactly the same to them.
Totally.
So. Yeah.
Okay. Cool. No, that's helpful. That's helpful. So, what was the most challenging? What was the most challenging?
Yeah. Sorry. I also want to say that for me, one of the more exciting things about, for instance, this PixelCNN method compared to HMM, is that it seems much more easy to improve on this result using this method than, for instance, HMMs, which are much more based on like hardcore mathematics and like probabilistic models, and it's very difficult. Like if you change something, you have to derive all the new formulas and stuff like that. And with something like this deep learning technology, it's very easy to try different things, try different parameters, combine things. If something new comes out, it's very easy to implement it. So I'm quite hopeful that this direction will, maybe not right now, but in the near future, will really improve.
Yeah, I mean, that sounds like a lot of the similar storylines that we're hearing in other research as well, saying like, hey, I was solving this particular problem with this particular approach, and now with a machine learning based approach, it's allowing me to try more different things, try different models, change those parameters. So I think we're seeing that across the industry, which is pretty cool. What was the most challenging part about working with this?
So one of the issues with this model is that, like I said before, that it predicts the next sample from a window of previous samples, and this means that the kind of setting in training and in synthesis is different, because in training, in this window of previous pixels, you use the actual pixels that are there, and in synthesis, you use predictions. So, and these predictions tend to be noisy because they have some error always, right?
Mm-hmm.
So, so you're actually not, the synthesis objective is actually not exactly the same as the training objective. and it's difficult to use this autoregressive process at training because it would be too slow. So this makes some of the training more difficult because it's kind of hard to tell whether your model is improving the actual synthesis or not. And then another issue very much related to this is overfitting. So in this case, especially because I have the data set is very small, and also the data itself is quite kind of limited. So yeah, there's not so much variation because it's kind of constrained by the different phonemes. So you only have n number of phonemes in the language, and you cannot really go very out of this range. So it's kind of simple data in a way. So one thing we did to avoid the overfitting issue, or reduce it, I should say, is to use a denoising PixelCNN. So what this does is we inject some noise in the input, and then we try to predict from this noisy input the clean output, so without any noise. And this kind of helps to make the system more robust to noisy input, so the kind of input you get when you predict with the model.
Cool. Yeah, it's an interesting idea of injecting noise into your model. I mean, it's almost, so I feel like it's, training or something like that in real life of saying like, hey, I want to get better at a sport or working out or whatever, like this physical conditioning. It's good to always throw unique challenges at the body so the body can adapt it. It has that feeling of saying, hey, I know that you do well with this kind of easy situation, so I'm going to make it a little bit weird and random and increase the challenge. That's a cool concept.
Yeah, for sure.
So what are you up to next, and what are you excited about?
So for this work, the next thing we want to do is first of all try it in English. So like I said before, Spanish is kind of an easy language for synthesis compared to English. So yeah, this will be another challenge. And yeah, apart from that, I think and that's kind of more in the short term, and maybe make some improvements to the model, but more in the long term, I would really like to focus more on expression, like modeling expression, and really having a expressive synthesis automatically.
So when you say expression, what do you mean by that?
So for instance, so the typical input to a synthesizer like this is kind of note score, but like very simple melody, not with a lot of details. So it would be nice if a system like this could kind of interpret a symbolic score, for instance, and sing it in a way that a human would. So decide where to put a vibrato, decide how to time all the phonemes, decide when to do a scoop, when to do a glissando, all things like this. And this is very much an open issue, I think.
Yeah, and that would be really interesting approach for that. So that's a pretty cool idea. Yeah. Anything else that you're excited about in terms of maybe either this general space or anything around that nature?
Well, I think it would be very nice if we could train these kind of systems from very few data, or very kind of, so in this case we recorded in a studio and it's kind of perfect conditions, but it would be very nice if we could take, maybe from a singer who has already passed away, and we can take some existing recordings and build a voice from that singer, or yeah, things like that.
Yeah, that sounds really awesome. I feel like I interviewed Bach creator, and it was kind of a similar concept, but around kind of the composition of music and how would Bach do compositions of music. And I just found it really interesting, is that they passed it like the happy birthday chords and whatnot, and they get past it at Twinkle Twinkle Little Star. It was just really interesting to hear an interpretation of how Bach might have played this music. And it's interesting. And we had talked about at the end of Jimi Hendrix and maybe playing kind of guitar solos on some of the similar stuff. And how would Jimi Hendrix play this this song? And it's interesting now to think of voice as well and saying, hey, how do you kind of include, you know, speaking of Jimi Hendrix again, like Jimi Hendrix could do the vocals and the guitar part, and putting all these pieces together to have some really interesting recreations. And I know that there's been some attempts that I've run into in the music industry, but I'm assuming that those attempts have been very manual processes and taking a lot of little different clips of people's voices.
Yeah, for sure.
Very, very difficult and time-consuming processes. But that sounds really awesome to me as well.
Yeah, and another thing that would be very exciting for me is that if this kind of singing synthesis technology would also become as popular as it is in Japan, for instance, but in the West. So I would love to see some like contemporary artists use this singing synthesis technology in their songs and really have it be used more here.
Yeah, this is slightly unrelated, but I find it really interesting. Kanye West released his latest album, and I think he did it on Tidal, and there was a bunch of controversy because what he did is he released the album and then he ended up deleting a song and re-adding a change to that song. And so he was kind of dynamically changing the album as it was kind of live in the store. And I think he got away with that a little bit because it was Tidal, and I think it wasn't technically released. And I don't know the music business well enough to know what was interesting about that. But what I found interesting about it, at least in the tech community, in the startup community, is that when we build software, at least when you often build software, you'll put it out in the market and then people will buy it, and then you are shipping updates to that software. And so it's this idea often that the customer has bought the rights to not only the software that you've built today, but all the subsequent updates that are going to come out for that software. And what I think is interesting about this Kanye West album is that there was an interesting article in TechCrunch saying, hey, it's kind of the first album that was a subscription. Like, I am buying the rights to the music that Kanye has selected as these 13 songs as he sees fit, as he sees his updates. You know, I think of bug fixes and patches and everything that we're used to in the software world. He's releasing, hey, I don't like this verse anymore, so I'm going to change it out with a new verse, or I don't like the title, like whatever it is. And it just gets my mind thinking about how I've always thought about how I would do music if I was musically inclined, which I'm absolutely not musically inclined. But it's always got me thinking of like, hey, I maybe would make an album that is a software, it's a SaaS model, software as a subscription. And then I'd probably be generating a lot of it with kind of machine learning and some of these artificial intelligence approaches. And it'd be really interesting to subscribe to the idea of a song. So instead of buying an actual exact song saying, hey, it's exactly this exact note at this moment with this exact same lyric, I wonder if the music of the future is a little bit more subscription-esque or SaaS model-esque, where it's saying, hey, I'm buying the idea of this song and the general melody of this, and I'm letting artificial intelligence kind of generate that song dynamically. And so I'm not necessarily always listening to the exact song, but I'm listening to something very similar that feels good. Kind of an abstract, crazy thought, but it's got my mind wandering as I listen to you kind of talking about your future stuff. So
that would be great. Yeah.
Like, you're buying access to Jimi Hendrix, right? And how he interprets any cool music, and he's just generating. So you pay $100 a year, and it's just you have access to that model. I don't know.
Yeah, very interesting.
Yeah,
we will see.
We'll see. But well, hey, I really appreciate being on the show. Thank you for taking the time of taking.
Thank you very much.
Yeah, everything, and it's been really interesting. And so anyone listening, I'll go ahead and I'll post links to both the project as well as the files, and we'll take a listen to it. But really appreciate you joining the show. Thank you.
Thank you.
All right, bye.
Bye. Thank you.